In this video, we'll discuss randomized controlled trials, a type of experimental study design that's very valuable in causal reasoning. In order to motivate randomized trials, let's remind ourselves of the medical study that motivated our discussion of causation, confounding, and causal diagrams. In this study, investigators examined the effectiveness of two treatments for kidney stone removal: an invasive open surgical procedure and a minimally invasive procedure. 350 patients received each treatment, and whether or not the surgery succeeded in removing the kidney stones was recorded. We saw that when we calculated the crude relative risk, it indicated that treatment A, the invasive procedure, resulted in worse outcomes. But we saw that the crude analysis was misleading because kidney stone size was a confounder. It was a common cause of both treatment and surgical outcome. We represented this with the causal diagram here at the top. Surgeons tended to use treatment A for large stones, and large stones were more likely to result in failure. To control for or adjust for the impact of the stone size confounder, in other words, to remove its influence, we performed stratification. We repeated our analysis within subgroups. This forced our comparison of treatments A and B to be fair. That is, within the strata, there was no difference in stone size between the two treatments. The stratified relative risks were better measures of the causal effect of treatment on surgical outcome than the crude relative risk was. So what we've seen so far is that one way to control for confounding at the analysis stage, once data have been collected, is to perform stratification. Stratification is nice in that it's straightforward, and it makes explicit that the confounding variables are being held fixed. However, it can be tedious if there are a lot of subgroups of the confounding variable, and particularly when there are a lot of confounding variables to consider. Another strategy for controlling for confounding at the analysis stage is statistical modeling. A widely used type of statistical model is called a regression model. These models provide a more general way to make comparisons while holding other variables fixed. These models work whether variables have a small number of categories or are continuous, meaning that they have infinitely many values. However, these models are not flawless, and like any tool, they can be misused. The modeler has to choose what variables to include in these models, and this can go wrong in a variety of ways depending on the causal structure of the situation. It turns out that more advanced tools for working with causal diagrams are helpful here, but we won't talk about that in our class. So aside from dealing with confounding at the analysis stage, it's often desirable to try to prevent confounding at the study design stage. One way to do this is with matching. This is the process of selecting subjects to match on characteristics that might confound the comparisons we want to make. So, for example, in a case control study, we could find a control for each case that matches on age and sex. The downside of matching, and also stratification and statistical modeling, is that we need to know and measure these confounding variables beforehand. Another way to deal with confounding at the design stage, and which is the main subject of this video, is randomization. With this strategy, we decide the exposure or treatment status randomly. For example, we might roll dice. We might assign treatment when we roll an even number, and we might withhold treatment when we roll an odd number for a patient. The major advantage of randomization over the other methods is that it can control for both known and unknown confounders. So let's take a closer look at why randomization works to control confounding. Say that we're aware of a number of known confounders. They're labeled here as C1 to Cn. All of these are common causes of the treatment and outcome, and we indicate this with arrows from each to the treatment and to the outcome. So even though we might feel that we've measured a large number of confounding variables, there's always the potential that we missed some, that we haven't measured all of the confounding variables. These unknown confounders are shown in blue as U1 to UM and they are also common causes of the treatment and outcome. Even though we don't measure them, these confounders can still bias our analysis of the true causal effect of the treatment on outcome. When we randomize individuals to different treatments, the value of the treatment variable, aka yes treatment versus no treatment, or version A versus B versus C, the value of the treatment variable is under our control. In terms of this diagram, this means that the arrows from each confounder to the treatment all disappear. This is because even though these variables were, in the natural world, causes of the treatment, in our experiment, we experimenters are the only cause of treatment. We experimenters are the only cause of treatment through whatever randomization device we use: dice, coins, or computer random number generators. Because randomization breaks the arrows from the confounders to treatment, they no longer confound our comparison. Even though these variables still affect the outcome, we don't expect that they will differ between the different versions of the treatment. For example, suppose that age was a confounder. We would not expect age distributions to differ between the treatment versions. And although age still affects the outcome, it won't bias our comparison of the treatment versions. So the key word in all of this has been expect. It's certainly true that just by chance, the treatment group could be younger than the non-treatment group. A strategy to prevent this is called stratified randomization. Say that we have two age categories of people, young and old, and we're thinking that age might be a confounder. We could gather all the names of the young participants and draw half randomly out of a bag to receive the treatment, and the other half of the young would not receive the treatment. We can repeat this process in the old. In this way, the age distribution is exactly balanced between the treated and the non-treated. So we have forced the age distributions to be identical, but the nice thing with randomization is that all of the other non-age confounders are still expected to be balanced between the treated and the non-treated. Another important issue in randomized trials is that of blinding. Blinding refers to the fact that participants should not know their treatment assignment, and certain investigators should not know patients' treatment assignments. If this blinding does not happen, confounding can creep back in. How? So we could imagine that some key variables that affect patients' measured outcomes are their emotions and the investigator's subjective evaluation of the patient's symptoms. If a patient is sad or anxious, that could result in worse outcomes. If an investigator is feeling strict when evaluating a patient's symptoms, that would likely affect the measured value of the patient's outcome. When blinding is carried out effectively, there are no arrows to any of these variables. We're still in the situation where there's no confounding because there are no common causes of the treatment and outcome. Now, let's imagine a situation where blinding was not carried out effectively. A patient knows that they were not treated because they somehow found out that they received a placebo drug. That likely would make them more anxious, worsening their outcome. Conversely, a patient who knows that they received the real drug might be more at ease knowing this and have better outcomes. From the investigator's standpoint, if an investigator knows that a patient was treated, received the real drug, they might unconsciously view symptoms as being less severe and thus report a better outcome for that patient. Or if they knew the patient was given a placebo, they might unconsciously view symptoms as more severe and report a worse outcome. Graphically, this introduces an arrow from the randomization device to these emotion and subjectivity variables, which reintroduces confounding. The randomization device is now a common cause of treatment and outcome through the pathway going through patient emotion and investigator subjectivity. This is why blinding is crucial in randomized trials. So, to wrap up, randomized control trials, also called RCTs, are often called the gold standard for estimating causal effects because they're able, if everything runs smoothly, to break the links between all known and unknown confounders and the treatment variable. This means that on average, we expect no systematic differences in confounder distributions between the groups being compared, usually treatment versus no treatment. Despite this, there are still many issues with randomized trials. The most glaring issue is ethics. Is it ethical to withhold treatment if there's some belief that the treatment is actually effective? These are deep issues that we have to ponder. Another issue is that full blinding can be hard to achieve in practice. Finally, non-compliance can ruin the very feature that makes randomized trials nice. In nearly every trial, there are participants who do not comply with their assigned treatment. They don't take the drug when they were assigned to, or somehow find and take the drug when they were assigned the placebo. People who don't comply with their assigned treatment are generally very different from people who do, in ways that tend to impact their health outcome. So, with non-compliance, confounding creeps back in. No study design ends up being perfect in practice, but randomized trials are still what we try to emulate when designing good observational studies.